Okay. Hello everyone. Today I'm going to present sliding window CRDT sketches. This is our work. I'm Dolev. My advisor is Professor Friedman. We're from the CS department, Technion, Israel. So let's start with the problem. We have a stream of items that arrive one at a time, and we want to answer questions as how many times does an item appear in the window? So for example here, how many times does the green square appears in the window? And we're not interested in the whole stream, we're interested in a sliding window. So for example, a time-based sliding window is the items that arrive in the last day, or the last hour, or the last week, etc. So that's the time-based sliding window. So we remove items from the window by their timestamps. Or we have a count-based sliding window, which is the last W items. So the last 1,000 items, the last million of items. So whenever a new item arrives, we remove the last item. So that's the count-based sliding window. And in our algorithm, we support both the time-based sliding window and the count-based sliding window. So we want to answer these questions. For example, how many times does the green square appear? Here it appears 2 times. In the window, so not the entire stream, just this window. Okay, so we're in a distributed model. So we have several nodes or servers, each receives its own stream, and we want to answer questions with regards to the whole stream and not just one stream of one server. And we want to ask any server that we want. We can pick any server and receive the same answer. And we want to ask how many times, for example, here the brown square appears in the last hour. So this is our window. And we want to ask each server that and receive the same answer. So that's our goal. So to do that, we need to communicate with each other. We need the servers to communicate. So here the first server sends a message to let the other know, hey, I got the blue square and the brown square. That's the new item that I received. And it sends messages periodically. Each message contains the new item that were received from the previous message till now. So that's how we communicate with each other, with the servers. So, and we do not want to send the items themselves, as we want to reduce the amount of volume that we send. So we'll send the change in the state. What happened? How the state has changed. So we send a table that represent these two items, the blue and the brown, to the rest of the servers. So we'll send a tiny sketch where we're doing sliding window CRDT sketches. So we'll send a tiny sketch that will represent these items to the rest of the servers. And they, in their turn, will merge this tiny sketch with their sketch. And that will represent their stream with these new items. So that's how they're going to share knowledge with each other. Okay, and that's how we can ask any server that we like and receive the same answer. So to answer this question, let's assume that these items, as you can see here, D3, all appeared in the last hour. And we want to answer how many times does the brown square appear. So let's pick a server. For example, let's pick the 4th server and ask this guy, how many times does the brown square appear? And as you can see, it did not receive any brown squares in its stream, but it will return us 4, as 4 brown squares appear in the whole stream, in the entire stream. So that's our mission. Okay, let's look at the requirements. Okay, so operation can always be accepted at any given node and answers immediately, so without communicating first to other nodes. Updates are propagated asynchronously to other nodes and are sent periodically. And in this work, we adopted the delta state CRDT approach. So as we saw in the previous slide, we'll send the change in the state as a tiny sketch and not the entire sketch and not the items themselves. And eventually, after all updates or operations have been notified to all nodes, they must hold the same step. And therefore, they'll answer exactly the same. So no different false positives, they're gonna answer exactly the same. So whenever a node received a delta state update in our protocol, it merges these updates in a deterministic manner, and the order of updates will not matter. The last sentence is not true to many sketches, but this is a requirement to our sketch. Okay, and of course it is very important that we'll be able to compose the message and send it to the rest of the nodes with little or no computation, as we want to do it fast. And it's important that the merge will be fast as well, because it happens periodically. We periodically send messages and merge them, the messages that we receive from other nodes to our sketch. So that's a key feature in our solution. Okay, let's look at the problem and then we'll look at the solution, at our algorithm. So this is the true frequency of the item that in the window. So in the example that we saw earlier, the brown square appeared 4 times. So the true frequency is 4. And we're a sketch, so we trade off accuracy to memory. We'll have a very small data structure, but we'll trade off accuracy for that. So we'll return an approximation. And we promise that. So for any node ni in time t, a delta approximation solution will always overestimate, and with probability of at least 1 minus delta, the frequencies will be the same. As the true frequency in the example we saw was 4, so let's say our approximation will, our sketch will approximate 5 or 6, for example. And with probability of 1 minus delta, it will return 4. Okay, so when we understand that, so we can now move to the solution. Let's look at the algorithm and the data structure. So as we said before, every period of time, let's call this period t, it's a user defined. So every t, we're going to send a tiny sketch to the rest of the servers that indicates what happened from previous message till now. So as this is a key requirement in our solution, we're gonna build around this. So we have W divided by T plus 1 tables. Each table represents an interval of time of T units of time. So for example, here the first table is from 0 till T units of time, and it represents all the items that arrived in this interval. And the last table, for example, here, it's from W units of time till W plus T units of time. So each table has T units of time. Okay, and inside the table, let's look what we have. We have the fingerprint, which represents the item. So we do not want to store the entire key as it consumes a lot of memory. So we're going to store a fingerprint. And here, that's the reason for approximation, as we have collisions in the fingerprint. But we'll soon see how the table itself looks like. It's not a regular hash table. Okay, so we have the fingerprints. We have the frequency that this item, for example, arrived 2 times in this time interval. This item arrived only once, etc., etc. And we have the timestamps when it arrived. So here it arrived. We have a timestamp of 1, which means it arrived at W minus T plus 1 time units. And the second number in this tuple is the server number. So it means that server that first saw this item, that received it in its stream, was server number 1. And then it sent it to the rest. For example, here we have this item appeared in server number 1 stream, and then in server number 2 stream. And then server, for example, if this is server number 1, this timestamp and this item was received by a message from server number 2 to server number 1. We'll see it soon again. So that's our data structure. And every t units of time, we send a table to all nodes. So let's look how that looks. So sending delta state changes is very easy without any computation at all. Great. So we simply send a table. That's the whole idea here with this data structure. So we can do it very fast. So we simply send the table, this tiny sketch, to the rest of the servers. And we do it every t. And the merge. Well, both of the tables are sorted, so we simply need to scan both of the tables. So first, we'll identify the correct interval we need to merge with. Here it's this interval. It could be 2 tables, it doesn't have to be 1, that match our received message. This is a message from server number 2. And here both messages are sorted, as I said, so we can simply scan both of them and merge these items like this. Okay. Now let's look at the logical view of the table. The actual view there, this table does not have any pointers, and it's frugal in memory, so it consumes significantly less memory than a hash table. So the table is separated into buckets. So here we have 3 buckets, bucket A, B, and C. And then each bucket has several chains. So here we have 3 chains, chain 1, chain 2, and chain 3. And each chain holds several items. So here we have item with a fingerprint A, C, and B. Okay, and how we map from an item to a bucket, a chain, and a fingerprint? Like this. We hash the key and receive this number, and then we divided this number into 3 parts. The first part is the bucket number, so here is bucket B, for example. The second part is the chain, so for example, chain number 1. And the fingerprints, this is the bits that we're gonna store in the table. So for example, 6 bits. It depends on the delta. So here we have, for example, fingerprint number A arrived 2 times, and that's the last timestamp. We have 2 algorithms, last timestamps and all timestamps, and we'll see them both very soon. So now let's look at the add and the query, and then we'll see the difference in these algorithms. So in this example, we have a window of 24 hours. We're going to send a message every hour to the rest of the servers or any topology that we want. And the time units are in minutes, to simplify the example. So we want to add this item, the star with this timestamp, and it's server number 1. So as we can see, we need to identify the interval, the correct interval. We can compute it. This is the last table here. And here we can see that a fingerprint already appears in the table. So we can simply add a timestamp and increase the frequency. And as we can see, we only store 5 as it's from the beginning of the interval. So it's only log t bits. Great. So that was fast. Now let's see the query. Okay, so in the query, we want to query an item. So we want to query a key. This is the fingerprints to make the slide more simple. And inside the query, we have the query interval. We can query the whole window, the 24 hours, and we can query any sub-interval inside this window. So it doesn't have to be the last one. It could be any interval inside this window. So we can ask from example, from 1 till 5, or in this example, from 23 to 25, whatever we want. Okay, so here we're gonna sum the tables that are, we're gonna sum the frequency that the table interval is within the query interval. If the table interval is partially in the query interval, we will not sum the frequency, as we want to reduce the error. We'll sum the timestamps, the correct timestamps that are within the query interval. So here the whole table interval is within the query, so we can simply sum the frequency like this and continue like this. And that's how we ensure we'll usually sum the frequencies, and just at the edges we'll sum the timestamps. Okay, so that's the query process. So, we give a query interval and can ask any interval inside the window, which is kind of cool. Let's look at the graphs. As I said, we have CRDT 80 and CRDT LT. We have two sketches here. The 80 is all timestamp. We store all the timestamps. As in previous example, we'll return to it soon. And the LT is less timestamps. We simply hold only the last timestamps. So we have a slightly higher relative error, as we can see here, but we have a smaller memory. So let's look again at query. Here it's all timestamps, as we store all the timestamps of a certain item inside the interval of the table, all its appearances. So if the frequency is 2, we'll have 2 timestamps. If the frequency is 5, we'll have 5 timestamps. Okay. And the LT is the last timestamps. We store only 1. Even if the frequency is 10, we'll only have 1 timestamps. Okay. So here we have a graph with relative error in correlation to the memory, and we have our sketches and swamp, which is the state of the art in the centralized setup. And as these are the parameters: Chicago 16 trace. This is a network trace, and with these parameters, and as we can see, we consume less memory than swamp. Another thing I need to mention here is that, as we can see, both algorithms have here the same memory, as it's an upper bound of the memory, but of course LT consume less memory than 80. However, we need to know the number of uniques to know the exact memory, and we do not want to assume that. So we have slightly higher relative error, but less memory as well. And as we can see, we consume less memory. For example, here it's 0.8 megabyte is enough, and to have a very small relative error. Okay, so in the previous graph here, the relative error was computed at the end of the trace. This is the relative error at the end, but we wanna query in a real scenario during the trace. So as we can see here, the error is quite stable, and it's important for us as we query during the trace and not at the end of the trace. So let's look at the variables when we vary t and vary w. So here we vary t. So these are the parameters San Jose trace with this window size and this window size. They're different, and we change t. This is 2 to the power, so 2 to the power of 9, 10, etc. And as we can see here, when we increase t, the relative error increases as well. CRDT AT increases slower, and CRDT LT increase higher, as the fingerprint size is this log W divided by T delta. So when we decrease the fingerprint size, we have less bits, we have higher collision. So we have more collisions, and that's the reason for the relative error. And the same with varying W. So this is 2 to the power. And as we can see, the relative error reduces. Do not have much time, so I'll continue. Let's look at the distributed setup. So here we have number node from 0 to 10, and we randomize a delay. So for each message, we choose a random number that indicates the delay of the message to show the delay of the network. Here we have 2 delays, and as we can see, the relative error increases as expected, but not that much. This is the distributed setup. We have the relative error in correlation to the transferred volume, and we can see that we have very low transferred volume, the amount of messages. This is with 10 nodes, And that's because we send in delta state changes. So we send a tiny sketch and not the items or the whole sketch. And a key thing here that we can ask any node and get exactly the same answers with all once they receive all the messages. So that's great. And our transfer volume is very small. Thank you very much.